Hello everyone, welcome to today's tutorial on SVD or singular value decomposition. So this is probably one of the most used matrix decomposition techniques around the world. So if you can apply it in genomics, in bioinformatics, and in many other fields. Now this is very popular because you can apply SVD literally on any matrix. I mean the matrix can be rectangular, can be square or anything. So let's dive in. Let's start with linear function. So why do we bother with linear function? It's because matrix multiplication is one kind of linear operation and it can be decomposed into three particular sub-operations based on which actually SVD has been developed. So let's first understand linear function. So the first property to be a linear function is if you have a function f, so f of x plus y is going to be equal to f of x individually plus f of y. This is the first property. So let's see if matrix multiplication actually follows this property. So we have this matrix and we have this vector and this vector x and y. So if we apply a multiplied by x plus y, we are going to get something like this. We can also apply this individually to x and y and then add them up. We are going to get the exact same thing. So the first operation is fine. The first property is done. What about the second one? So as you can see, in the second one, we have f of cx equal to c of fx. So what is c? C is just a constant scalar value, nothing else. So let's see if this holds. So let's assume that this is matrix A, and then we have x, we have c right here. So you can apply c into x first, which constructs this 20,5 vector, and we can apply a on that, and we are going to get this nice vector right here. We can first apply ax and get 8,3, and then apply the scalar multiplication by c, which is 5, and we are going to get the exact same thing. So this actually proves that matrix multiplication is actually a linear operation. Now, this is not a generic proof. I am basically giving you an example here, right? A theoretical proof should be much more rigorous, but this is just to build up your intuition, nothing else. So let's now visualize SVD. So as I said before, we want to actually map a linear operation using some sub-operations. So let's assume that we have this nice circle object right here, which have some points. So each point is basically a point vector on the 2D space, as we understand. Now what we can do is, we can apply a matrix multiplication on these points. So if we apply matrix multiplication, there will be some transformation of the points, and suppose the points become like this. So this nice tilted ellipse is actually formed. So this is a linear operation, because matrix multiplication, as we saw before, is a linear operation. So now let's see if we can actually replicate this operation into three small operations. So first of all, we multiply these points by this matrix, which is a rotation matrix. So this matrix basically rotates the points. So you can see that the points have been rotated in the clockwise direction, right? Then we have another matrix, which is a diagonal matrix. As you can see, that diagonal elements are non-zero and all the other elements of this matrix will be 0. If we do this, then there will be some scaling. So since this value is bigger than 1, there will be stretching in the x-axis, and since this value is smaller than 1, there will be compression in the y-axis. That is what we are seeing right here. Finally, we can apply another rotation. This is again a rotation matrix. If we apply this, then this particular ellipse will just move anti-clockwise direction. Okay, so that means a matrix A, any matrix A can be actually decomposed into U, this sigma matrix, which is a diagonal matrix, and V transpose. Okay, now that we sort of understand the intuition from a high level about what's going on, let's understand orthogonal matrix first, because this is important for our SVD. So this is an orthogonal matrix. If you multiply an orthogonal matrix by its transpose, then you are going to get the identity matrix, where all the diagonal elements are 1 and everything else is 0. So this is true for both Q transpose Q and QQ transpose. And we know that if we multiply a matrix by its inverse, then it also produces the identity matrix. That means Q inverse 1 is actually equivalent to QT for orthogonal matrices. So here you can see each row vector is perpendicular to all other rows. For example, this row vector is perpendicular to this row. So how are you going to understand that? So if you multiply or if you dot product this row vector with this row vector, it will be 0. That means the angle is 90 degrees. Similarly, if you multiply this row vector by the last one, it will also be 0. Same goes for column. So every column is actually perpendicular or orthogonal to each other, and every row is also orthogonal to each other. So this is actually a pictorial representation of that. If you dot product x and y, you are going to see a 0 result, and that is why you can see that these two are actually perpendicular to each other. That means orthogonal vectors. So the U and V matrix that we obtained previously, the previous slide, for rotation, scaling, and rotation, those U and V are actually both orthogonal. That is number one. And number two is typically the orthogonal matrices are actually used for rotation. So if you multiply some object with a orthogonal matrix, then there will likely be a rotation in that object. So let's see how SVD is applicable for all matrices. So this is the formula for SVD. This is a random matrix. It's a 3 into 3 square matrix. And if we apply SVD on it, we are going to see these three things coming up. So I would want you to pay attention right here. You can see that this is a diagonal matrix. It will always be a diagonal matrix where everything else will be 0 except for the diagonal. Now, even in the diagonal, you can see a 0 element right here. Okay, so for this matrix, we have only two singular values. So these values are called singular values. Okay, so this is the first singular value, which will be the highest. This is the second highest. So you should remember that the first value of the singular matrix should be the highest. Then comes the second one, next highest. Third one will be next highest. And maybe if you don't have any other singular values, then the rest will be 0, basically. You can also apply this to a rectangular matrix. So for example, you can see this matrix to be decomposed into 3 into 3, 3 into 2, and 2 into 2 matrix. And ultimately, this sigma matrix right here has two singular values. And this is actually a rectangular matrix, so it doesn't have any real diagonal, but we can still take the short diagonal starting from the left end. So it also has two singular values, right? So the number of singular values a matrix has after its decomposition actually determines its rank. So if you have like two non-zero singular values after decomposition, then your rank of the matrix is 2. So what does matrix rank actually mean? So matrix rank actually denotes the number of linearly independent rows or columns. So what is linear independence between rows and columns? I will show you with an example. So for example, you have a matrix right here. So row 3 is actually equal to row 1 plus row 2. That means row 3 is a combination of row 1 and row 2. Similarly, you can check out column 3 right here. It is actually an addition of column 1 and column 2. So row 3 and column 3 are actually linearly dependent. They are not independent. So we have only 2 rows and 2 columns, which are linearly independent. So this is a rank 2 matrix. You can similarly look at here. You can see that row 2 right here is actually twice of row 1 and row 3 is -1 of row 1. That means if you simply multiply row 1 with some scalar value, you can get row 2 and row 3. That means row 2 and row 3 are actually linearly dependent on row 1. So the only independent row here is row 1. That means it's a rank 1 matrix. Now we don't need to look at the column here because a matrix cannot be less than rank 1. So obviously we are going to take rank 1 here. Now here is the interesting thing. You can have a rank 0 matrix as well, but only if all the entries of the matrix are actually 0. That is the only case where you are going to get a rank 0 matrix. So I hope this is clear. So another thing I want to mention is if you can formulate a row using addition and scalar multiplication of other rows, then that row is linearly dependent on the constituent rows. So, I mean, only two things are actually applicable here. One is if you add those rows up, or if you multiply with some scalar value and maybe also add. Okay, that is basically the definition of linear dependency in terms of matrix rows and columns. So right now, we have talked about SVD implications, but now we are going to talk about something more interesting related to SVD. So this nice matrix right here, we applied SVD on it, and these three things came up. So this is the left singular matrix, right singular matrix, and then this is the singular matrix itself, right? So if we look closely here, we can actually take the first singular value, the first column of this blue matrix, and the first row of this green right singular matrix. If we multiply these three things, we are going to get back this nice 4 into 4 matrix. Now, some people are a little bit confused here. You can think of this as a 4 into 1 matrix, and you can think of this as a 1 into 4 matrix. So if you multiply 4 into 1 and 1 into 4, we are going to get back a 4 into 4 matrix. And if you look closely, this matrix is not that far away from the original matrix. Let's go further. We can now add the second element as well, which is obviously the second highest, as I said before. So second column, second singular value, and second row. And we can add these two things up. We are going to get back this. So this is actually much closer to this matrix compared to what we achieved previously. We can now add the third term as well. If we do that, we can see it is pretty close. Now the thing is, if you are satisfied with this approximation of the original matrix, then you can just use these three components to construct the original matrix. This is the most interesting thing, and you need to remember this, that in order to reconstruct an original matrix, we don't really need all the components. Maybe if this matrix were like 1000 into 1000, we could have reconstructed it using maybe first 10 components. I don't know, right? I mean, not exactly, but approximately. So this is the basis for image compression and dataset compression, and we are going to talk about that shortly. Finally, if you add up all the four components, then you are going to get back the exact matrix that you started with right here. Okay, now let's talk about data compression using SVD. You have the basics now, so you know. First of all, we have this nice image. Let's talk about image because we understand image better, and it's a 2D thing. We know that. So it's an 800 into 400 size image. So we apply SVD on it and you get these three matrices, and their shapes are 800 into 800, 800 into 400, and 400 into 400. Now, the thing is, suppose we sort of say that, okay, if we take only two components, then we can reconstruct the image approximately and it will be a good reconstruction. Then what happens? So originally, this is the space requirement for the image. We are taking two components. So from U, we are going to take the first two columns, that means 800 into 2. For singular matrix, we are going to just take the first two values. So that will be 2. And finally, from VT, we are taking the first two rows, which are 2 into 400. So total, we have 2402. And if you actually do the math, you are going to see that this 2402 actually is 99% reduced compared to this original size. So this is a huge reduction in memory or in space. That's the thing. Now, the main question is, how many components are you going to take? Here, randomly, I'm saying that you are taking two components, but will it be enough? How would you actually understand this? So this can be understood by a nice formula. So let me clarify this. So these are all singular values. So this is the first singular value at the very left. This is the second one, second to the very left, and so on and so forth. So these are singular values, and we know that they are in the decreasing order. Now, if we want to actually understand the explained variance of the data or the image using maybe first two components only, we are going to add sigma 1 square, that means singular value 1 square, plus sigma 2 square, and we are going to divide it by all the sigmas, they're squared. Suppose that gives us a number, say 0.8. That means 80% of the variance of the image have been explained by, the first two components only, right? Which is pretty good. Now, here's the interesting part. So when are you going to be satisfied? How much variance do you need to be explained actually? So this is, normally people are satisfied with greater than 95%. But if you want to be really accurate, then you would expect something above 99%. That is the thing. So those of you who know about PCA or principal component analysis knows that this is very similar to what we do in PCA. Actually, the rows of VT are the PCs from this image or from this data set. So if you think of this as a data set, then there are 800 samples and there are 400 there are 800 samples and there are 400 features for each of these samples, right? So you can arrange them into a matrix and you can do SVD. And if you want the first three PCs or principal component axis, then you are going to take the first three rows from VT. But for those of you who don't know PCA, you don't have to worry about this now. I'm going to make a separate video on PCA because it's an extremely important topic to cover. So just to give an example, suppose you take the first 5 components, you are going to get maybe a blurry image. Then you take 10, a little bit better, 15, a little bit better, 20, maybe good enough. It's not a high resolution image, but it's good enough to understand what's there. So now it's a good time to talk about symmetric matrices. So first of all, look at this matrix, you can see in this matrix Aij is equal to Aji for all cases. So what do I mean by that? That means this element in row 2 and column 1 is the exact same as this element of row 1 and column 2. That means we have just transposed it. Similarly, the element in row 3 and column 1, which is -2, is equal to the element of row 1 and column 3, which is again -2. So if you have this reflection type of property with respect to diagonal, then that is called symmetric matrix. And in a symmetric matrix, if you do transpose, it is going to be equal to that matrix itself. So transpose means making the rows of the matrix into columns. So if we do that, if we make this row into this column, then make this second row into second column, and so on and so forth, still nothing changes. Now, most matrices are not symmetric. For example, if you look at this matrix, if you do transpose here, I mean, you are actually making this row into this column, making the second row into second column. So it doesn't remain the exact same as the B. So BT not equal to B, so it's not symmetric. So finally, if your matrix is not square, if it's a rectangular matrix, say 4 into 3, it's never going to be symmetric. That's the thing. So why am I talking about symmetric matrices here? It is because it is necessary to understand this, to understand the SVD solution process. Now we are going to talk about how exactly are we going to get the U matrix, the VT matrix, and the sigma matrix using SVD. Now SVD is actually a generalized version of Eigen decomposition. It is because Eigen decomposition is only applicable for symmetric square-shaped matrices, right? You cannot apply this on any other matrix. That is the thing. But the issue is, in order to solve SVD, we are going to use Eigen decomposition. Now, in this video, I'm not going to talk about how you do Eigen decomposition. It is because then this video is going to be very long. I have talked about Eigen decomposition in detail in one of my videos. So check out the video. I will provide the link in the description. So definitely check that out if you want to understand the SVD solution process. So SVD can be applied to non-symmetric rectangular matrices as well. So it's more generalized. So we can basically use Eigen decomposition to solve for SVD, which we are going to do right now. This is the result you get if you decompose a symmetric matrix A using Eigen decomposition. So you are going to get Q and Q transpose, which are both orthogonal matrices. And you are going to get something of lambda, which is very similar to the sigma matrix that we saw for SVD, or the singular matrix, whatever you want to call it. Now, suppose we want to apply SVD on a matrix A. Let's keep it general. Let's make it M into N. We can construct two other matrices. One is the A transpose A matrix, the shape of which is N into N. And the other one is A transpose, which is the shape of which is M into M. Now, both of these matrices are going to be symmetric. Now, what I want you to do is, I want you to take any matrix A, whatever you like, and do these two things, ATN, AAT, and then you check yourself to convince yourself that, okay, indeed, A transpose A and A transpose will always be symmetric. Since A transpose A and AAT are symmetric, we can apply Eigen decomposition on these, right? So let's see what happens if we do that. So first of all, we know that A can be decomposed into U, sigma, and VT if we apply SVD. So we have two of these. If we apply transpose here, everything will be like reversed like this. And UT and U both are orthogonal matrices, and they will basically cut each other and become the identity matrix, which is equivalent to multiplying by 1. That means we are getting something like this. Okay, very good. That means this ATA can actually be expressed as this. And this is what we're talking about. If you actually look at the similarity between this right-hand side part and this right-hand side part, you are going to see that Q is actually equal to V in the Eigen decomposition, and the lambda is actually equal to sigma transpose sigma. That means we have successfully been able to detect the V matrix of the SVD through Eigen decomposition of A transpose A. And this is squared of the singular values. So if we just take the square root, we are also going to get back the singular values. So what about U? If you want to do U, then you need to take A transpose. You can do the math like this, and you are going to get something like this. So you have U and U transpose right here. And this also has very similar shape to this one in the Eigen decomposition. And so here for this context, Q will be equal to U. Similarly, we can actually take A transpose, and if we do the math like this, we are going to get this kind of thing. So you know that Q is actually U and lambda is actually sigma transpose. So, I mean, we have already obtained the singular values from here. We don't need that. We only need the Q. So Q equal to U and we can get the U. So this is how simple it is. You just take A transpose A transpose, do the decomposition using Eigen, and after doing that, you get U from ATA, you get V from ATA, and you get U from AAT. And if you take the lambda value, and if you take the square root, you also get the singular values. So that is, my friend, is SVD. So feel free to like and subscribe to the video and check out our channel. And you can donate to our channel via the link given in the description. Thanks very much.